Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of the Astronomy Department at Foothill College, and it's my pleasure to welcome all of you around Silicon Valley and around the world to this lecture in the Silicon Valley Astronomy Lecture Series, now in its 21st year. We're delighted to be able to bring you distinguished astronomers discussing their latest research. This series of talks is co-sponsored by the Foothill College STEM Division, the SETI Institute, the Astronomical Society of the Pacific, and the University of California Observatories, which includes the Lick Observatory. Past lectures can be found at this very same YouTube website where you're now tuned in to our lecture tonight. Tonight, we are delighted to welcome back one of our favorite speakers in the series, Dr. Michael Brown. Dr. Brown is a professor of planetary astronomy at the California Institute of Technology, where he teaches classes from introductory physics all the way to the study of the solar system. He is the author of a best-selling and award-winning book, How I Killed Pluto and Why It Had It Coming, which was the topic of the previous talk he gave in this series, which was all about his discoveries that led to the demotion of Pluto as a planet. He has discovered dozens of dwarf planets and interesting objects at the edge of the solar system. And he received many prizes for his research, including the Kavli Prize in Astrophysics for his fundamental contributions to our understanding of the extent and the history of our planetary system. He and his research group spend their time searching for and studying the most distant objects in the solar system of which we are part. And in addition to his award-winning research, Dr. Brown is also an outstanding pioneer in the outreach of astronomy. He has given lectures all around the world, and I've known him since graduate school, where he already showed a great interest in how to share astronomy with the public. So tonight, he is going to speak to us about Planet 9 from outer space, searching for a distant planet in our solar system. And he's going to take questions at the end of this talk. So I encourage everyone to send questions to our email address, astronomy@foothill.edu. So now, ladies and gentlemen, it's a personal pleasure and a professional privilege to be able to introduce to you Dr. Michael Brown.
Thanks, Andy. It's great fun to be able to talk here again, even if I'm not quite here again. But I've always had a warm spot in my heart for this particular talk series. I remember the first time I spoke here was very shortly after our discoveries of the very largest things out in the Kuiper Belt. And it's been fun to continue to update this audience on what we're learning about the outer solar system. And I have to say that this one that I'm going to be telling about you today, this search for Planet 9, is, I have to say, I think it's the most exciting thing that we're up to. So the story of this search for this new planet out beyond Neptune really is a continuation of some of the same stories that I have been telling before, since I have been speaking on this stage, which is the exploration of the outer solar system, the understanding of what is further and further out there. But the beginning of that story, I would say, really started in as early as 1781. So I want to set you back, not 1781, but 1780. In 1780, if you looked out at the sky, and if it was a night like it is tonight, you could look out at the sky and see all of the planets further away than the Earth. You can see Mars right now rising. If you're here in California, it's just rising over in the east. You see Jupiter and Saturn setting in the west, and that was it. Those were the planets beyond the Earth. And if you go look at things that were written back in that time period, I have not been able to find anybody writing about, speculating about, thinking about the fact that there might be more planets out past Saturn. I just don't think it was in the idea of the cosmos of people at the time that there could be another planet other than these obvious ones that we see out there. This all changed in 1781 when William Herschel was using his new telescope, and it was the best telescope in the world at the time. It had made very, very crisp images, so he could see stars as little points of light. And he was mapping the locations of stars across the sky. And he went to one location, and well, the star was not a little point of light. The star was a little bit of a blur. And that's strange, but not entirely strange. There are many things up in the sky that are not points like stars. There are galaxies, there are nebulae as we know them now. He was careful though, so we went back the next day and that little blur moved. And that was it. As soon as you realize that something is moving in the sky, it's not a star, it's not a galaxy, it has to be part of our solar system. So Herschel immediately knew it was part of our solar system, but he didn't really know what it was. It even for him, who had just discovered Uranus, even for him, it took a while to really believe that what he had found was a planet. He thought maybe it was a comet. People knew about comets coming and going. He just didn't quite know what it was. One of the big questions that people had before they really were convinced that this is a new planet was, how far away was it? What sort of orbit does it have around the sun? Does it go in a circular orbit like planets do? Or is it like a comet where it comes close to the sun and goes far away? And right now we just happen to be looking at it far away. This question was answered. It took a while, but this question was answered in about 1820 by a French astronomer named Alexis Bouvard. And Alexis Bouvard doesn't get nearly as much credit, in my view, for all the cool things he did for the discovery of Neptune, which is coming up. Alexis Bouvard, let me show you this book that he wrote. When you're in Paris in 1820, you get to write these really boring titles with some really spectacular subtitles here. So it's basically tables of Jupiter, Saturn, and Uranus. He was basically publishing a book of where Jupiter and Saturn and Uranus were in the sky, and then he gets to put all of his accolades down at the bottom of this: member of the Academy Royal of Sciences, London and Munich, and all these things that really we should go back to doing that. I would love to be able to write things like that. What he did though is he tracked the position of Uranus in the sky, and he then realized that other people in the past had seen Uranus before actually Herschel had in 1781. Other people had charted it as a star and didn't realize. They didn't do like Herschel and go back and look the next day and see it move. They just charted it as a star. And so Bouvard went back, he found one. He said, okay, if that's real, let's go back some further. And there's another one, and there's another one. And he went all the way back. I'm going to show you this. He went all the way back to 1690 was his first observation that he found of Uranus. So here's the discovery of Uranus in 1781. And you can see data starting in 1781, a ton of it. But before 1781, there's a decade earlier, there's before that, there are a lot of observations of people who accidentally saw Uranus and didn't recognize what it was. What Bouvard did was write down a bunch of math that you can see here, and he used that math to predict where Uranus should be. And we all know that planets go around the sun and they go on ellipses around the sun, but they're always tugged a little bit by the other planets. So Uranus is being tugged along by Jupiter and Saturn. And so to really figure out exactly where Uranus should be, you have to take into account the gravity of Jupiter and Saturn. So when you do that, with all this math right here, you get a prediction of the location of Uranus. And when you do that prediction, there are errors. You can see he says errors here. And sometimes it's a little bit in front of where it's supposed to be, sometimes behind, sometimes in front, sometimes behind, a lot of behind. There's some in front again. And Bouvard, being a theoretical astronomer, one of the preeminent theoretical astronomers of the day, was very much like the preeminent theoretical astronomers of these days. And you've probably had some give talks. And if you've had them, they would probably say the same thing, is that the errors that you see here are not errors in my theory. The errors are all due to the astronomers who made the measurements, and astronomers need to make better measurements. He did say, okay, there's a chance, maybe there's something else going on there, but really, I blame the astronomers. It's all their fault. They'll do better. So astronomers worked hard to make better measurements. Starting here in 1820, which is when this was published, they did 20 years of very, very careful measurements, and it was still not in the right place. By 1840, it was clear, I think, to all the astronomers who were paying attention that something was happening, that there must be another planet out beyond Uranus that was tugging at the orbit of Uranus and making it move a little bit faster sometimes, a little bit slower sometimes. The problem was, in 1840, nobody knew how to figure out where the planet was. 1846, another French astronomer, Urbain Le Verrier, came along and worked out the math to be able to use these data that you're looking at right here, where Uranus is in its orbit, to pinpoint the location of his new planet. He predicted he did the math, he predicted the location, and he sent that prediction to the Berlin Observatory, and the Berlin Observatory opened up their telescope and found Neptune in the very first night of looking for it. To me, this remains one of the most amazing stories in science of an observation, a prediction that something was wrong, remeasurement, reprediction, and then triumphant discovery. And there are very few stories as good as this one, I think. It's such a good story that, of course, Le Verrier got really, really famous at the time. He's one of only, I forget the number, I think it's like 90 people whose names are carved into the Eiffel Tower in Paris. It's pretty good if you can get your name. Like, he didn't go up and do graffiti and carve his own name into it. Somebody else put it there for him. Pretty good. There's a statue of him in Paris, right at the Observatoire du Paris. He's standing, pointing straight north, looking right up towards Luxembourg Gardens and towards the center of Paris. Like, it's a pretty good place of honor. It got pretty famous for finding, as they said at the time, finding a planet at the point of a pencil. So what happens, of course, if anybody gets really famous for finding a planet, all the other astronomers out there are like, I'm going to do that too. I'm going to go find me a planet. So almost literally the next day, astronomers everywhere started predicting the existence of new planets. They used the same data. They used data, new data that suggested maybe Uranus and Neptune were not quite where they were supposed to be. Maybe there's still something else out there, and they made these predictions. And there were, I tried to count them all one time, and I found as many as 35 independent astronomers making these predictions. And well, turns out none of them are true, but the most famous of these predictions came from American astronomer Percival Lowell. Percival Lowell was predicting the location of what he called planet X. Again, he thought it was due to perturbations of Uranus and Neptune. He made predictions, and he went off and went to a telescope, looked, didn't see it, made new predictions, went and looked, didn't see it. He eventually founded the Lowell Observatory in Flagstaff with a mission to go find this new planet. Lowell passed away before this search came to fruition, but after he passed away, the Lowell Observatory hired Clyde Tombaugh and told Clyde Tombaugh, go find this planet. Clyde Tombaugh went to the sky, looked at the location, was searching the region where the prediction of the new planet was, and he took a picture. Looks like that. No planets there. So he was like, well, I don't actually know what a planet is supposed to look like. So the only way I know to look for a planet is to take a picture and then take another picture and watch it move. Did anybody see it move? No, nobody saw it move. Let's try again. Here it is. There it is again. Did you see it? No. One more time. Still didn't see it? Fourth time's a charm, I'm sure. There it is. There it is. These are the discovery images of Pluto. Pluto was more or less in the location where Percival Lowell had thought that planet X should be. And this is how science can sometimes go wrong. Clyde Tombaugh was looking for Planet X. Planet X was supposed to be massive. Clyde Tombaugh found something in about that location. And so the answer was, well, that must be Planet X. This thing in the sky must be huge. So if you go to the New York Times headline for the day of the announcement of the discovery, ninth planet discovered on the edge of the solar system, lies far beyond Neptune. So far, so good. Sighted January 21st. Observatory staff there spots it through special photo telescope. Awesome. Well done. The sphere, possibly larger than Jupiter. Oh, possibly larger than Jupiter meets predictions. That's the bad part. So possibly larger than Jupiter? No. This is wrong by a factor of 250,000. Meets predictions? Kind of. That was the problem. It was predicted to be there. It was found, therefore it must be it. So turns out, of course, that Pluto is not Planet X. Turns out that Uranus and Neptune are not being perturbed at all. There's nothing massive out there changing their orbits. And Pluto was just a lucky find by Clyde Tombaugh. And it happened to be, well, I shouldn't say just lucky. It was a careful find. But it was by luck. It happened to be in one of the earliest places he looked, by Clyde Tombaugh, who was doing this thorough survey of the sky. So the other weird thing about Pluto, if you can find it again, it's one of those things. It's one of those things. It's this little guy down here. It's really small when you look at it in these images. And people were confused for a while about why it was so small. But after a while, it became apparent that the reason it's so small, this is actually a surprising fact that a lot of people don't know. The reason it looks so small in these images is because, well, it's because it's really small. How small is it? People often are misinformed about just how small Pluto is compared to the rest of the solar system. And I like to just throw this in there just to do a little size of planets education. You never see a picture that looks like this of planets. But let me tell you what it is. Here we have Jupiter here in the background, the big one. Saturn, even without its rings, quite big. Uranus and Neptune. The terrestrial planets, Mercury, Venus, Earth, Mars, quite small. Even these little guys. Here's Ceres, the largest asteroid, and the other asteroids that are big enough to be one PowerPoint pixel in through here. Usually when you see drawings of planets, they're all kind of the same size because it looks better on your daughter's lunchbox that way, as far as I could tell. But they're not. They're really wildly different sizes. And here's, if we now throw Pluto on there, Pluto's tiny. Pluto really does not fit this pattern of giant planets: Jupiter, Saturn, Uranus, Neptune. Oh, there's Pluto. But at the time, in 1930, when it was discovered, there was kind of nothing else to call it. And even though it progressively over the years, we realized it was smaller and smaller and smaller and smaller until 1978, when we realized just how small it really was. You know, it was weird. It was this oddball out the edge of the solar system, but okay, we could just keep it a planet. There was nothing else to call it. This all changed as we started to really explore the outer parts of the solar system. Here's a view that I also like of, now here are the orbits of Jupiter, Saturn, Uranus, Neptune, Pluto, with its really weird elongated orbit that sometimes takes it inside the orbit of Neptune, but usually outside the orbit of Neptune. You know, Pluto was so weird. Not only does it have that non-circular orbit, unlike the planets, it also, if you look at it on the side, it's tilted with respect to the planets. Super weird. But again, you know, what else are we going to call it? There's nothing else out there. So you might as well call it a planet like the other planets and just move on. Well, there are other things out there. It turns out that as of today, we know of something like 4,000 objects in this ring of material that we now call the Kuiper Belt out beyond Neptune. And if you put all the orbits of all those objects in the Kuiper Belt on the plot, you realize that Pluto fits exactly with the rest of those objects in the Kuiper Belt. Pluto is not some oddball at the edge of the solar system. It's just yet another Kuiper Belt object, and happened to be the first one that was discovered. Excuse me. It's this beautiful picture of what the solar system really looks like, and it really drives home the important thing is that there are these four massive giant planets dominating everything, and then many, many tiny objects out there beyond Neptune that are the debris that was left over from beyond, from when the solar system was formed. Everything in the solar system makes sense. Everything in the solar system is where it's supposed to be. We can predict their positions just by looking at the gravity of the things that we know. Well, okay, this was true until about 2003. In 2003, everything changed. And everything changed with the discovery of one weird object. That one weird object, oh, I was going to show you, I've got ahead of myself, forgot to show the sizes. Here are the sizes of those objects in the Kuiper Belt. Pluto, in case you lost it, Pluto is that one. And there are objects that are about the size, there are smaller ones. Pluto really does fit very nicely with this Kuiper Belt object. That one weird discovery from 2003 was, well, here are the objects that I just showed you. That one weird one was the object that is known as Sedna. Sedna is on this orbit that is huge compared to the rest of the Kuiper Belt. Sedna takes I have been talking about Sedna for nearly 20 years now, and I suddenly forgot how long Sedna takes to go around the sun. Sedna takes something like 10,000 years to go around the sun on this tremendously elongated orbit. And what's strange about Sedna is that not just the elongated orbit, but that it never comes close to the giant planets, any giant planet at all. It is really, even though on this scale it doesn't look so, it's really kind of pulled away from the rest of the solar system. And that's very strange. Something had to have pulled Sedna away from the rest of the solar system. And in 2003, we had no idea what that something was. We speculated at the time that probably it was a star that came screaming by the outer part of the solar system, pulled Sedna a little bit out of its orbit, left it as this fossil remnant of when we had stars. Excuse me. When we had stars streaming by, but we didn't really know. What was strange is we kept on looking for more objects like Sedna, and we were wildly unsuccessful finding them until finally one of my colleagues, a pair of my colleagues, found a second object a little bit like Sedna, and then we started looking at other objects, not the ones that were necessarily pulled away like this, but objects that went on these really distant orbits. And we realized something really strange. Here's the really strange thing. All of the objects that go on these very distant orbits, here's now the same, this is the orbit of Neptune here in blue. Sedna is one of these. I am going to forget which one it even is. I think it might be the purple one right here. That's Sedna. All of these other, I can tell by how far away it is. There's Sedna right here. That's Sedna. All of these other objects are very distant. They're on these very elongated orbits. And what's really strange about them is they all look like they're pulled away from the sun in one direction. It's a very strange thing. There really is nothing that we could think of that would pull everything away from the sun in one direction. And what's also strange is if you take these objects and you tilt them on their side, although take the orbits and tilt them on the side, you realize that not only do they go off in one direction, they're all actually tilted up a little bit in the same direction too. It really is as if there's something out there that's tugging them along their way. This is where 5 years ago, I walked down the hall to my friend and colleague, Konstantin Batygin, and I showed him some of these data. I was like, what the heck is going on here? And you know, it's funny. I'm really sorry. I got to cough just a second. Okay, we'll stop that. It's funny because every time anybody finds anything weird in the outer solar system, it's just like those astronomers from 1846. It's like, there must be a new planet out there. So most people would immediately jump up and down and say, new planet, new planet, new planet. And we absolutely did not want to do that because, you know, we knew the idea that there's a new planet out beyond Neptune was crazy. And people had been saying it for 200 years and they'd all been wrong. And we didn't want to be the same sort of people. So we started looking for any other thing that could be tugging these objects in their orbits. And sadly, the answer is we couldn't come up, well, maybe not sadly. We tried everything we could think of, and we could not find any other process that would pull all of those objects in one direction like that, except for a massive planet on an elongated orbit. So we did out the math and we realized that it works. I say we did out the math. Actually, Konstantin does all the math and I just kind of look and pretend like I know what he's talking about. But we did the math and it all worked out perfectly and these things were supposed to be elongated. And we still were kind of dubious that this really made any sense. So we did a massive set of computer simulations where you take, well, let me actually show you these massive computer simulations. You take a planet, here you can see it in red barely. This is the orbit of a planet. Neptune is way inside of here. Each of these little blue things is a test particle, a Kuiper belt object that we put on a very elongated orbit. And the question is, can this planet, after 4 billion years or so, pull all these objects into orbits that are all kind of lined up? So what should it be? Well, we were pretty sure that we knew what was going to happen is that this planet would pull a bunch of objects into orbits that look sort of like this after 4 billion years. So we let the computer run, and you see a couple things. First off, very quickly, you'll notice that things you notice that things don't run as nicely on Zoom as they do in real life. But here we go. That things disappear really quickly. First thing does is the planet ejects tons of these objects. The other thing is that orbits change a lot. The presence of this giant planet is pulling orbits towards it. It's pushing some away, but we're waiting for, and also you can see that these green ones on the inside just sit and spin. Nothing much happens in there. It's only the distant ones that are really affected. And we're waiting for ones to get caught right here, like this one. This one gets, oh no, it does. This one gets caught. Nope. These guys, that one? No. This one get caught? No. That one? No. Nothing's getting caught. So our bright idea that everything was going to get caught over here is wrong, turns out. We miss one critical point when we did the math. This time I'll blame Constantine because he did the math. We missed one critical point, which is that we made a simple assumption that was important for doing the math, which is that we were going to ignore orbits that cross the orbit of the giant planet because those are hard to mathematically handle. And it turns out all of the ones that are stuck, that are saved, are the ones that are cross the orbit of the giant planet. This is really strange, and we were surprised at first, but now we realize what's going on. What happens is that, as you know, when a planet goes around the sun, it's like a comet going around the sun. It spends most of its time way out here. It goes slowly, and then it goes here, it goes faster and faster, and zip through there like that, and slow, and then zip. So it's almost always out here. Same thing with these guys. These guys spend all their time out here very quickly and through here. What that means is that nobody spends too much time in through here where they're close to each other. It's not that these guys get stuck in these regions here. It's that these guys are the only ones that have survived after 4 billion years because they spend the least amount of time close to this giant planet. The objects that were over here, well, the planet spends most of its time here. The objects would spend most of their time there. They would get close to that giant planet. They would just get ejected. So instead of having them all this way, they were all this way. Once we realized what was going on, we redid the math, and of course it all made sense, and we realized that we should have done it that way to begin with, but it was nice to have done these computer simulations to see. So now we realize that the existence of these objects in orbits like this meant that there had to be a planet in an orbit like this. And if you actually turn the planet and the objects on their side like we did before, you realize that like the objects being tilted in one direction, the planet has to be tilted in this direction too. So this was pretty cool, and we were like, okay, we should write this down. We should publish a paper. We should tell everybody about it. But we were a little bit reluctant, and we were a little bit reluctant because, well, we really didn't want to be the 36th and 37th astronomers to stand up and say, we just found a giant planet at the edge of the solar system, and be wrong, because that would seem pretty silly. So we sat back and we thought, how can we prove to ourselves that this makes sense? And one of the ways that we did it is, one of the ways you do that is you make predictions. You make predictions of things that you didn't try to explain. Explaining things is easy. Coming up with a theory, well, easy. Coming up with a theory that can match the data that you already know is a lot easier than making a prediction about things you don't know and having that come true. But making that prediction about things you don't know is really the right way to do science and convince yourself what's going on. So we made some predictions. One, we would find more and more objects aligned like these objects, but that was going to take a while. But we made a really interesting prediction that almost killed the entire theory, which is that we realized that in addition to these very distant objects that were lined up, there should also be another set of objects that are not lined in the direction that the lined up ones are, but actually perpendicular and also on orbits that are perpendicular to the plane of the solar system. You know, we said Pluto is crazy because it's tilted by about 20 degrees. I'm talking about things that are tilted by 90 degrees to the plane of the solar system and oppositely directed as these objects here. It's a crazy prediction because we didn't know of any objects like that that existed anywhere in the solar system. And so it was sufficiently crazy. And because we didn't know of these objects, we were almost ready to throw our theory out the window. It just didn't, if it predicted that these objects must exist and we didn't know of any. And it turned out the only reason we didn't know of any is because I forgot to look in the right place. This is so Constantine's fault for doing the math wrong. My fault for forgetting to look at another set of objects. I was actually only looking at the objects that stay pretty far away from the sun. When I looked at the objects that come close to the sun, but go far, far away, there were 5 objects that were exactly like I described. Their orbits are tilted by about 90 degrees and they go really far away. And what we didn't know is how they were lined up compared to these objects here. And so Constantine came into my office and I was like, okay, I'm going to plot these on the screen for you, and we're going to see, are they lined up exactly where we think them? And remember, we want to see them perpendicular to where the things are now. I didn't show him this plot, but I showed him a plot that did this. And the answer is, there they are. Those 5 blue objects are exactly what we predicted. Their orbits are perpendicular to the plane of the solar system and also perpendicular to the alignment here. And I think at that moment, Constantine and I both had our jaws hit the floor, and we went from, this is a cute theory that's kind of fun to think about, to, oh, there's actually a giant planet out there at the edge of the solar system, and we're the only people that know it's out there. So we wrote this paper explaining these observations. It turned out to be the most downloaded paper ever in the Astronomical Journal. It was downloaded by something like 200,000 people, 7 of whom probably understood the math that was in it. But everybody downloaded it, which was kind of fun to watch. And we set out to do 2 things. One is that this was really preliminary, just like an existence proof. There is a planet out there. We really wanted to figure out where that planet was and describe what it was like, and then we wanted to find it. So that first process, where it was, describe what it was like, really came about by just continuing to do more and more and more computer simulations and matching them more and more precisely to the data. And we learned a couple of really interesting things. One is, I should tell you one more thing, is that as we continued to do that, people kept on finding more and more distant objects, and the more and more distant objects all match. So the first prediction was that there should be these perpendicular things, and that worked out perfectly well. But the second prediction, that's I think the stronger one, is that more and more distant objects should be lined up correctly, turned out to be true. So that's pretty exciting. So we put all those in together and we can make some really good predictions. One is how massive Planet 9 is, how massive it has to be to make those effects. And the answer is, well, our first preliminary results were that it had to be about 10 times the mass of the Earth, which is an interesting mass because Neptune is about 17 times the mass of the Earth, Uranus 14.5, Earth turns out is precisely 1 times the mass of the Earth. Planet 9 is midway between the Earth and these giant planets. We think that that means it's like a gas giant, but we did learn as we did more and more of these simulations that it's actually 10 was our rough number. A much better number we now know is about 6. It's about 6 times the mass of the Earth with an uncertainty of about 1, we think, which is pretty good that we can, without having seen it, we can already do a pretty good job of seeing how big it is. We know about how far away it is. It's something like 500 times the distance from the Earth to the sun. That puts it at something like 15 times further away than Neptune, and on a inclined and eccentric orbit that makes it have those effects on the outer solar system. So this has been the predicting of where it is and how big it is has been years and years of analysis. But it's really interesting to think about something that's this size sitting out there in the outer solar system, because if I go back to this plot of what the planets are, and sometimes when I say, oh yeah, there's Planet 9, we think there's a new planet, people say, oh, we're just going to argue, is it a planet, is it not a planet? But I just want to remind you, there's Pluto, where people who are misinformed continue to argue. Planet 9 is this big. Planet 9 is the 5th largest planet of our solar system. Planet 9 is it or isn't it a planet? It is pretty unmistakably a huge member of our solar system that it'll be incredibly fascinating to learn about once we actually go find it. So how are we going to find it? Well, as I said, we do these computer simulations, we match, we do, it's actually been 4 years of developing what I think is some pretty sophisticated computational and mathematical methods to turn the observations into predictions. And it feels a little bit like, okay, maybe this sounds a little full of myself, I shouldn't say it, but it feels a little bit like Leverrier. Therefore, I think I should have my name in the Eiffel Tower. No. It's a little bit like Leverrier, who turned the observations of where Uranus was into a prediction. We are turning the observations of where these Kuiper belt objects are into predictions of where the planet should be. So where should the planet be? Well, it looks, how are we going to find it and where should it be? So this is not the slide I want to show. I want to show you this slide, which is where it should be. This is our latest and greatest, we like to call it the treasure map of where Planet 9 should be as we look across the sky. So here's the sky. Here's the celestial equator. This is the whole sky shown in a single projection. Celestial equator is like this. The ecliptic, where the planets are right now, goes like this. Actually, Jupiter and Saturn are right over here right now. Is Mars in the Milky Way right now? Mars must be right here. The Milky Way galaxy is this region in through here that you can see. Planet 9 is somewhere along this path right through here. And the colors show you the probability of finding it in any particular location along this path. So highest probability out here because that's the part of the orbit where Planet 9 is farthest away and it moves the slowest. So that's where it's most likely to be. Lowest probability over here where it's close and moving the fastest. You can also see this plot above is how bright Planet 9 should be at any of these locations in the sky. When it's further away, it's faint. So this the high numbers mean it's faint. When it's further away, it's faint. When it's closer, it's brighter. And you can see quite a range. For the astronomers out there, these are magnitudes. At its very brightest, it's 18th magnitude. I bet there are people watching this right now who have telescopes in their backyard that can see 18th magnitude objects. Sadly, I don't think it's 18th magnitude. That would have to put it close to the sun, close meaning it's only 300 AU away. So still not very close, but it would be at its closest position to the sun. It would also be in the southern hemisphere. So if you're watching from the southern hemisphere and you have a big telescope that can look to 18th magnitude, go take a look. I don't think it's there. I think we've ruled that part out already. Most of these predictions are between about 18 and 22-ish. At the faint end, it could be as faint as 24. Okay, so for those of you who don't speak astronomer magnitudes, that means really big backyard telescopes, modest size professional telescopes, pretty big professional telescopes, the biggest professional telescopes. That's your calibration point. So we're somewhere between backyard telescope and the biggest telescopes we have on the Earth. The good news is we're not beyond that range. If it were coming up to numbers like 27 and 28, I would say we don't have the telescopes to find Planet 9. Go give it up. Somebody's have to do this next generations. But we do have those telescopes, and here are those telescopes. Normally, when I give this talk in the past, I would talk about this telescope. These are telescopes I use a lot. These are the Keck telescopes on Mauna Kea. But right next door to the Keck telescopes that I use a lot is my favorite system. Well, used to be my favorite system for looking for Planet 9. This is the Subaru telescope. The Subaru telescope is the Japanese national telescope, and it's fantastic because they have built the biggest astronomical camera currently on a telescope in the world, and it can cover huge areas of sky all at once, and that's fantastic. But we now know, back when we first thought we were looking for Planet 9, we didn't have this prediction of how bright it was. We thought it was pretty faint, and we thought we were going to need this biggest telescope. We now know that a lot of this range of predicted magnitudes requires not the biggest telescopes in the world, but can be found with a modest-sized telescope. My favorite modest-sized telescope in the world is over here. You can't see it. It's on Maui. It's on the summit of Haleakala, not on the summit of Mauna Kea, and it's the Pan-STARRS telescope. Pan-STARRS is some terrible acronym that I can't even remember. Panchromatic something else. Terrible. But the Pan-STARRS telescope did a survey of the whole sky that it could see from Mauna Kea over the course of about 6 years. And it took, every year it took something like 10 to 15 images of every spot in the sky. And if you look at a spot in the sky where it took 10 to 15 images of every spot in the sky, you will see that there are stars, there are galaxies, and then there are what astronomers like to call transients. Transients are any time where you see something in a spot in the sky where you didn't see something before. There are a lot of reasons you could see something in a spot in the sky where you didn't see something before. It could be like the mundane reasons, like a Z equals 10 gamma ray burst or something boring like that. Or it could be something interesting, like something in the solar system. An asteroid moving across the frame is only there once. It's a transient. Could be, the merger of two black holes making a little flash. All these sorts of things might be a little flash in the sky. There are a lot of little flashes in the sky. And if you look at all of them in this one little patch of sky, tiny little patch of the sky, you might see something that looks sort of like this. This is one little 2-degree patch of sky. 2-degree patch of sky is if you hold your arm at as far as you can and make a little circle with your hand like that. That's about 2 degrees in the sky. That's about how big this is. Every one of those little dots is a transient that Pan-STARRS found over a 5-year period. Okay, some of them you might kind of guess what they are. You can see this big splotch right here. Well, that's where there was a bright star and their little spike coming from the bright star, but the computer software still finds it as a little dot. More stars. Garbage, I don't even know what these streaks are, but they're clearly something. Sometimes you see these little streaks here. Who knows what these little streaks are? In this frame, however, is the most massive known dwarf planet in the solar system, Eris. Anybody see it? Well, what's it going to look like? I'll tell you, over the course of 5 years, Eris goes on a path that looks like this. Every one of these little loops is a 1-year loop. 1, 2, 3, 4, 5. This is 6 years. Over the course of 6 years, Eris makes these loops across the sky. The loops are because it's the retrograde motion of as the Earth overtakes in the orbit and then it comes back again. So to find Eris here, you would have to figure out which, if any of these, match this particular orbit. And to find it without knowing that it was there and not knowing the orbit, you would have to find which, if any of these, match any arbitrary orbit in the sky. I'll show you. Turns out Eris is there. Those are all observations of Eris by Pan-STARRS across this 5-year period. Eris is bright in that magnitude system that I was showing you about. Eris is about 19th. That means it's not quite bright enough to see in most backyard telescopes, or even very few backyard telescopes, but it's plenty bright to see on modest-sized telescopes. And it's only a little brighter than some of the predictions of Planet 9. So the question is, can we take observations like this and process them to find unknown objects in them? And the answer, turns out, is yes. It is a computationally humongous task. There are trillions of these little dots in the sky that are the transients, and we're looking for the small number that might fit an orbit of an object across the sky. We have a bank of computers working on processing all of the Pan-STARRS data in the track of Planet 9, and we're getting there. I actually just made this next plot from this afternoon. Here's what we have done so far. It's an ugly plot because it was never intended to show anybody. But these are all the fields we've looked at. It's the same. If you notice, this same swath across the sky. We basically covered this part, which is the biggest part, and we covered the galactic plane down here. There are a couple gaps because, well, I did the Milky Way galaxy first because I thought it might be hiding in the Milky Way galaxy. So I did this chunk, and then I started doing this chunk, and the seams aren't good. I'm going to have to go back and fix the seams. And I'm missing a spot here because this is data that are being processed right now. But these little chunks just finished today. And within 6 months, we'll have the whole set of data from Pan-STARRS. Each one of these little blobs that you can't quite see very well doesn't just show you where we've looked, it actually shows you a fake Planet 9 that I inserted into the data that was found by the algorithm. So we have 10,000 fake Planets 9 inside there based on our simulations. And with any luck, we have one real Planet 9. I will tell you, it's not in any of the data we've looked at so far. There was one object, there's one like right here that we found there where 7 points were just perfectly situated to be an object just about right. And I went back and looked. So then once you find something that might be real, you go back and look at the raw data, and you could tell that 2 of those detections were just glints from a star. One of them was a streak from a satellite, and like, it's not real. So far, no hits on the Planet 9. But I would tell you, I know what it's going to feel like, because I did accidentally almost convince myself I found Planet 9 once, because I have all this fake data in here. And I have to make sure that I don't confuse the fake data with the real data. But one time, 7 of my fake data points matched with 1 real data point. So it made 8 data points. And the real data point was first. And I was only checking the first data point to see it was fake. And it was a real data point. And I was like, it's real. And it was perfect. And it was right where Planet 9 should be. And I called my family in to come look at it. And I was like, oh yeah, that's fake. Never mind. But it was pretty exciting. So with luck, this is going to happen. Is it really going to happen? Well, I don't know. Pan-STARRS is going to peter out right around 21.5. So we'll finish all these objects in here. 21.5 will still leave these most distant predictions. These faintest ones could still be hiding out there, and we'll miss them. And in fact, as you've seen, we've gone through this whole section and through here. Maybe we'll find it here. I was really hoping we'd find it in Pan-STARRS. I really felt like the history of the discovery of Uranus. You know, Uranus was discovered in 1781, but it was seen as early as 1690. Neptune was discovered in 1846. It was seen by Galileo. Pluto was discovered in 1930. It was seen in photographic plates taken at the request of Clyde Tombaugh in 1916. Eris, that I just showed you, was discovered by me in 2005. We went and traced it back to images that were from 1950. It was imaged in 1950. If we had known how to take all those old images, process them correctly, we could have found Eris much earlier. We could have found Uranus earlier. We could have found Neptune earlier. It seems to me like we should be able to do this. It seems to me like this is the era when we shouldn't have to go to a telescope and take pictures to find stuff. It should be all there. I think Planet 9 is hiding in the data somewhere, and I still think we're going to find it by processing data before we find it by going to a telescope. Nonetheless, if it is this faint, we're going back to this telescope, and then we really are going to this telescope, the Subaru telescope on the summit of Mauna Kea. It's got this ridiculously large camera. The camera is so large that it is even larger than an anime character. And this is the camera. This is not a telescope. This is the biggest lens in the world. It was made by Canon for the Japanese telescope. And the electronic detector is up here. It covers, well, okay, remember I was excited about things that cover this much of the sky. It covers about this much of the sky at once. It's a tremendous amount of sky for a telescope that size. It can cover really faint objects. So Konstantin Batygin and I have been heading out there yearly at the right time of year to take a look at it. Here we are at that telescope. The camera's way up there at the top. Konstantin, he's a theorist. He probably shouldn't be at a telescope. You don't want to zoom in on this picture because he'll be embarrassed to see that as a theorist at 14,000 feet, he has to be breathing oxygen because he gets loopy at 14,000 feet. Real astronomers don't need oxygen at 14,000 feet. So that's why I'm not having any. But there we are. We're observing it. We will continue. We're going to be out there in January, taking a look again, January, February, to cover some of those regions where the fainter things are. And I think, so if not Pan-STARRS, Subaru, and if not Pan-STARRS or Subaru, because maybe we just miss it at the moment when we're looking. Maybe it happens to be in front of a bright star right when we looked. It's always possible. If not these 2 telescopes, then the backstop is the LSST, the Vera Rubin telescope, which will be online pretty shortly. And when we started this project, I used to say, "Gosh, I hope we don't have to wait till then." But now it's actually coming up pretty soon. And so one of these is going to find it. And I'll tell you, at this point, there's been so much new data and so many new calculations that the probability that there is no planet 9 out there, to my mind, is as close to zero as you can imagine. There really has to be a giant planet out there to describe the things that we're seeing, to explain the things we're seeing out in the outer solar system. And I think it is only a matter of time before we find it in old data, we find it in new data, or we find it in this brand new telescope that's going out there. And I just want to end with a plot of where it might be in the sky. If we end up finding it in the Subaru data, it's right here. It's basically in this cosmic battleground between Orion the Hunter and Taurus the Bull, and Planet 9 is right there in the middle. And I kind of hope that turns out to be true, because I just kind of think that it would be delightful to explain to people, this new planet is out there. You can't see it, but go look at the one constellation everybody can track down, Orion, and look at this location in the sky. This is where we've been looking with Subaru. We've covered a pretty good chunk of the Subaru region. We still have more of it to do, but I think, as I said, I think it's out there. I think we're about to find it. So I just want to leave you with one really interesting thought from the title slide. So of course, some people will recognize this title slide as the movie poster from the absolutely fabulous movie Plan 9 from Outer Space. When I say absolutely fabulous, I mean the worst movie ever made. If you haven't seen it, it's good, because it's the worst movie ever made. If you go to Wikipedia and look at Plan 9 from Outer Space, it is literally called on Wikipedia the worst movie ever made. Some people think it's so bad that it's good. It's not. It's actually just bad. Like, it's on YouTube. You can try to watch it. I dare you. It's terrible. So there's vampires and there's space aliens, and there's I like to think this is Constantine. It kind of looks like Constantine if you think so. But what's really interesting, so this is Ed Wood. This is 1959. This is still when Pluto was well and good a member of our planetary system, and yet there is this graveyard scene in the movie where they're digging up the zombies because the space aliens made the zombies come to. I tried to watch it. I don't really know what happened. But Ed Wood made this poster in 1959, and he was a brilliant director. Could be the worst and the best all at the same time. But this movie poster, if you zoom in to the graveyard scene, it's kind of astounding. Like, look at that. If you look up, there it is. R.I.P. Pluto. I think Ed Wood knew even back in 1959 how this was all going to play out. It's okay, Pluto. We will have a real ninth planet, and I think we're going to see it soon. And I will be happy to take questions.
Well, thank you very much for that wonderful tour of what might be in our future. The large member of our solar system that we can truly call Planet 9. I want to now encourage people to send questions, if you haven't already, to the email address that's showing. It's astronomy@foothill.edu. And I'm going to turn things over to Dr. Jeff Matthews, the astronomy instructor at Foothill College now, who has been looking at the questions that have been coming in. Don't stop sending them. He will be looking at the ones that come in as well. So let me now turn things over to Dr. Matthews.
Thank you, Andrew. I really appreciate it. And thank you, Dr. Mike Brown, for the great talk this evening. And so I would also like to thank all of the members of the audience who have been sending in questions. So, and I'm just going to apologize right now. We're not going to be able to get to all of them. We'll be able to take 8 or 9 questions here. And so here is the first question that we have. And a bunch of people have asked questions along the lines of this one. So this is a question from Lana asking, what do you think about the possibility that it's not a planet, but instead a brown dwarf or a tiny black hole? And with also the added question, what's your best advice for a current undergraduate astrophysics student?
Okay, so
2 for 1 there.
Okay, so 100% certain it's not a brown dwarf, and the reason why is that if it were a brown dwarf, it would be so close that you could see it with literally any backyard telescope. I mean, it's that a brown dwarf that close. Plus, brown dwarfs are massive. Brown dwarfs are something like 10 or more times more massive than Jupiter. Planet 9 is 20 times less massive than Jupiter. So if there was a brown dwarf there, it would basically rip the whole outer solar system to shreds. So there was this paper a year or two ago proposing that perhaps Planet 9 might be a black hole. So we know about the existence of Planet 9 only because of its gravitational effects on the outer solar system. So I cannot rule out the possibility that it's a black hole. All we know is that there is something that's 6 Earth masses out there, and we know approximately what its orbit is. So it could be a black hole, it could be a planet, it could be, as I like to say, a 6 Earth mass hamburger. We don't know. Is it a black hole? No. I'm trying to think of a kind word to say, but I'm not going to say it. I'm just going to say it's a silly idea. The reason it's a silly idea is because the argument is, well, the reason we don't see it is because it's a black hole. That's the argument. The reason we don't see it is because the sky is a big place. It's faint, and we haven't searched the whole sky yet. The fact that we haven't seen it is zero evidence for it being a black hole. And I just, for those who've been following astronomy, I would like to point out that like there are plenty of planets that we know of in the universe where we only see the gravitational effects, where we don't actually see. So most of the original planets discovered around other stars were discovered by radial velocity, where you just see the wobble of the star. That's just gravity, just gravitational effects. We don't all sit around and say, well, we don't see it, maybe it's a black hole. I mean, yeah, maybe it's a black hole, but it's not a black hole. Probably also not a hamburger, although it's a delicious thought, I have to admit. Advice for undergrads. I'm going to forget exactly what the question was. Advice specifically for what? Because I could give advice to undergrads all day long, which is what I do all day long.
Astrophysics students.
Astrophysics. Advice for astrophysics students is do your homework. Let's see. Is there better advice? But do your homework. My advice is, man, you're in a great undergraduate major. I actually didn't major in astrophysics as an undergraduate. I was a physics major, but it was pretty fun too. But if you are interested in astronomy and you can do it, and if you go off and get your astronomy PhD, it is I think it's the most fun thing that you're allowed to do and get paid for in the world. I actually still can't really believe that people pay me to sit around and do all this cool stuff. The other cool thing is that astrophysics is a fun major, even if you end up not doing astronomy. It's a great background. It's a great preparation for almost anything technical that you might want to do. So I have students of mine get their PhD in astronomy and in planetary science, and have ended up doing many other things besides just academic astronomy and academic planetary science. So it's a great major because it gives you technical background for all kinds of things. And it's super fun. I'm like who would not want to spend their time really trying to understand how to apply physics to the universe? I mean, really? Is there anyone who wouldn't want to do that all day long? Nope, I don't see anybody. Okay.
I have to agree with your advice there on this issue. It is a lot of fun. So here is a next question from Les asking. You touched on terrestrial, aka rocky planets versus gas giants. Do you have any speculation on the material composition of a theoretical Planet 9?
Yeah, it's a hamburger. It's pretty clear. No, this is relevant to the last question though, which is, again, it's 6 Earth masses, and that is really all I know. But that doesn't stop us from speculating. It's a good phrasing because it is speculation at this point. But it's speculation guided by what we know about other planets in our universe. So when we look at other planets around other stars, we see planets of this size. We don't have any other planets in our solar system between Earth mass of 1 and Uranus at 14.5. So we don't know in our solar system what that might be like, but in other planetary systems, we see these things. And typically a 6 Earth mass planet tends to be like a miniature version of Neptune rather than a large version of the Earth. Tends to be a icy core with a big gaseous envelope as opposed to a big rocky chunk. I also think, and this is also speculation, and someone may have asked this too, which is, how did it get there? This is related to how it got there. I think actually Planet Nine formed in the solar system in the same region as Uranus and Neptune. And then it just got a little bit too close to Uranus or Neptune or to Jupiter or Saturn, and it got flung outward. And it has been basically flung outward and hanging out at the edge of the solar system, lurking, waiting for us ever since then. That is such an uncontroversial idea that we actually wrote papers about a fifth giant planet and how it would have affected the early solar system long before we even thought about Planet Nine. We were writing these papers. We tracked them through the formation and through the ejection from the solar system. We never really thought very hard about what happened when they left. Turns out they can stick around, I think. Might not be true, but that's at least our speculation.
Okay, so we have another question from Al here asking, could these orbits on one side originate from an observational bias from observatories predominantly viewing at certain times of the year?
Yes, so the answer is they could, and that is a huge thing to worry about in astronomy, are observational biases. Because if you notice, they all come close to the sun at the same location, which means the same location in the sky, which means the same time of year to be looking at them. That time of year, it turns out, is right now. So many of these objects were discovered in November. Sedna was discovered on November 11th, in fact. That's today. I think it's November 11th. I have to go back and check that. It might be Sedna Discovery Day. 11. I named them after their day of discovery, but I might not be remembered that right. But anyway, so if you could imagine, like, you had bad weather every other time of the year and only good weather in November, you could imagine that could be the case. November is really not the best weather month pretty much anywhere on the planet. Certainly not Mauna Kea, where many of these were discovered. Certainly not in the southern hemisphere, where many are discovered. So the first thing to notice is probably not. It doesn't really make any sense, but it's still a hugely important question. So to answer that question, I actually spent a couple of years doing an analysis, taking every single observation of every single object that had been discovered in the Kuiper Belt, figuring out when they were detected, how they were detected, what they could have detected, and doing an analysis and asking the question, could the objects that we see now have come from a uniform distribution, but it's just bias that we're seeing? And the answer is, we can rule that out at the 99.8% confidence level, which is, I would say, pretty good. So the answer is no. It's a question that is 100% worth asking and really being careful about. But we now know for certain that can't be a problem.
Okay, great. And now, so here's a question. Several people have asked similar questions to this one, so I'm just going to pick one version of this. Have people ever tried looking for Kuiper Belt objects or other objects like Planet Nine indirectly using occultations in various ways? So occultation in radio of, say, the cosmic background radiation, or occultation of stars.
So it's a great question, and it's a great way to think about things. So the difficulty is occultations of any specific object that you care about in the sky are exceedingly rare. They're so rare that, like, when we want to, we occultations are great because, so an occultation, if people don't think about it, as a star is right here, the object goes in front of the star blinks out, star reappears. And so by timing how long that star has disappeared, you're actually measuring the size of the object, the chord of the object there. And so they're really important. So astronomers spend a lot of effort predicting when an occultation will occur, traveling to where on the Earth one will occur. The last trip I took was last December 28th. My daughter and I drove to Phoenix to observe an occultation of an asteroid that's the target of the Lucy mission to the Trojan asteroids. And so we really wanted to know how big it was for the Lucy mission. So we drove over there and participated in a big occultation event with many, many astronomers who were trying to observe it. But what that tells you is occultations don't happen very often. You have to really get lucky to even be able to see one. So you're not going to be able to find one by accident, find an object by accident, unless there are so many objects that occultations are happening frequently. So it is possible that if you look at smaller and smaller and smaller objects in the solar system, eventually you'll get to the size where occultations might be relatively frequent, such that you could watch one star and see it happens. We haven't reached that ability yet, and people keep talking about it. Like maybe we can find really small Kuiper Belt objects by just staring at particular stars and waiting for them to flicker, but it hasn't happened yet. And so it someday, but it won't happen for Planet 9 because the probability of any star doing it is low. But once we find Planet 9, occultations will be a really important thing to measure its atmosphere, to see how big it is, and to learn other things about it.
Okay, Dr. Brown. So now I have several questions from people sort of asking about other alternative hypotheses. So some of these are names that I'm not familiar with. So somebody mentioned work by Anne-Marie Madigan. Somebody mentioned work by a group called AUSIS. I'm not sure if I'm reading that correctly.
Both of those. So Anne-Marie Madigan had a really clever idea. She was working, actually, I believe she was working at NASA Ames at the time. Is that true? No, she was at Berkeley. She was somewhere up in the Bay Area. And it was right early on when we were first realizing about the existence of Planet 9. And she had an explanation for some of these very distant objects at the time when we didn't realize that all the distant objects were lined up. There were some other things about them. They were all tilted in little weird ways. And she had this very clever idea on how they could get themselves all tilted the same way, basically due to self-gravity. And once we realized that actually that's not what's going on, it's not that they're all just tilted in some weird way. They're all actually pointed in one weird way. And her self-gravity idea simply doesn't work with the current observations. It would have worked if it had been what we knew of at the time. So I still think it was a clever idea, and it's a cool thing that probably happens somewhere in the universe, but it's not explaining why these things are lined up in this way. The AUSIS observations were all about that bias that we talked about earlier. They early on were the ones who were trumpeting most loudly about this observational bias, and which is good. They should, and I think we have pretty thoroughly showed that it's not an issue. They still, it's a little bit to be a little mean here. It's a little bit like those people after Leverrier found Neptune. Everybody else tried to do something. They really, so we said that there's a planet, and astronomers always, if you find something cool and say it's out there, the next best thing you can do is show that somebody who had this cool result did it wrong. And so they really wanted to be wrong. And part of their argument is that their observations themselves are incredibly biased because they did a survey that basically only looked at two patches of the sky. They found a lot of objects in those two patches of the sky, but it's incredibly biased because they only looked at two patches of the sky. That's why we use all of the observations that people have done. So their argument still remains, but we've proved that there's bias, and the answer is yes. But just because you only look west every day and you see the sunset in the west every day doesn't mean that the sun actually sets everywhere and you just happen to be looking west. It really is that's where these things are.
Okay, so we're coming up on just our last couple of questions now. And so we have a question from Gary asking, and several other people actually had various variations on this, wondering about would it make more sense to be searching in infrared versus visible light? And several people emailed mentioning some things like JWST.
Yeah, so all good questions. So JWST, HST, space-based telescopes are going to be fantastic for studying Planet 9 once we find it, but they're terrible for searches. They look at tiny, 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 tiny little areas of the sky. So they're not designed at all for searches. They're designed for studying kind of individual objects or small areas of the sky. Interesting question about infrared versus optical versus radio. So right now the technological sweet spot is in visible, and just like the light that your eye can see. And there are two reasons for that. One is that's where the sun is the brightest. We're looking at it in reflected sunlight, and so we want the most sunlight. So the sun is brightest in the yellow as we see it, so it's going to reflect the most there. And just as importantly, our technology for detecting light at those wavelengths is fantastic. All of those digital cameras that all of you have really fed into making the astronomical cameras better and better and better. So these huge cameras like that one that I showed you from Subaru have benefited from decades of commercial digital cameras. And so we can build those better. We can build anything else. It is true, though, that as the technology improves, not in the infrared will never reflect enough light. But as you move further to the radio, at radio wavelengths, you'll start to see not the reflected sunlight, but the heat coming from the object. And that matters a lot. Maybe not for Planet 9, but possibly for Planet 10. And the reason why is because we're looking at reflected sunlight. Reflected sunlight has to go all the way out there. It's getting fainter as 1 over r squared as it goes all the way out there. It has to come all the way back. That's another factor of 1 over r squared. That means it gets, every time you move twice as far away, you get 16 times fainter. That's terrible for trying to find something that's really far away. The heat coming from Planet 9, well, it gets a little cooler as you go further out, but probably not much because it's probably mostly internal heat. But as it moves further away, it only gets fainter as 1 over r squared. So eventually, that thermal emission becomes a better way to do it. Right now, our telescopes, our radio telescopes for doing broad surveys of the sky aren't great, but they will be soon. So as time goes on, radio telescopes might really give us our best view of what else might be out there besides Planet 9.
Okay, and so now going into our final question for the evening. And again, I would love to thank all of the people, dozens of people who emailed in questions and for the Q&A. And I'm sorry that we can't get to all of you. So our final question here is actually related to the idea of commandeering some of the deep space probes. So could any of the deep space probes, such as the probe that photographed Pluto, help detect Planet 9?
Yeah, so it's always a great idea to think about alternative ways of doing things. So again, these probes, they're designed to be super small, super lightweight, so they don't have huge telescopes or huge cameras on them that are very good at finding things. They're really good at flying close by and studying it once you know where you're going. And sadly, Planet 9 is probably a U-turn for New Horizons, so it's going the wrong direction right now. But there are clever ideas of repurposing probes. My favorite one is actually the Cassini spacecraft. Of course, it's gone now, but the data are still there. And one of the very first, I think, really clever idea coming out of France soon after we published our paper was the realization that one of the things that Planet 9 will do is, even though it's really far away, it will very lightly perturb all of the planets in the solar system. And the amount of perturbation kind of grows the further you get away from the sun. And if you could measure precisely the distance to a planet over time, you would see this oscillation of the planet as the planet goes around the sun. If Planet 9 is here, as the planet goes around the sun, it's pulled a little bit toward it over here and not here, and it goes further away here. So it makes this kind of stretching. And if you could measure that, it would point to Planet 9, and you can. So what they realized is that the Cassini spacecraft in orbit around Saturn, sending back signals to the Earth, is basically giving you a precise distance between the Earth and Saturn every time it makes a communication back. And an analysis of those data, the preliminary analysis suggested it was just on the verge of being able to do it. The new in-depth analysis is really close. They they sort of detect a whiff of something maybe, and completely independently of us. They don't use any of our data to say where it should be. It's basically right in our path where we predict it should be, and it's right at about the distance we think it should be, and it's right around the mass we think it should be. But it's right on the edge. It'd be too bad. It'd be really nice if Cassini were there for another 20 years. We'd really have that information down well. But there are other clever things you could do. The best thing you could possibly do, I've been proposing this to anybody who'll listen, so if anybody's there, here's what you do. Send a brick into orbit around Saturn, send a brick into orbit around Jupiter, and just have those two bricks talk to each other and measure the distance between Jupiter and Saturn. The hardest thing about the Cassini measurement is the Earth is actually moving around too much due to the uncertain masses of asteroids that fly by. But Jupiter and Saturn don't get kicked by asteroids. So if you could just basically measure that Jupiter-Saturn distance continuously, you would have Planet 9, you would have any other planets out there, it'd be fantastic. So if anybody's got bricks that can talk to each other across space, come talk to me.
Well, thank you very much for that wonderful talk. So often in astronomy, we hear only about things after they've been discovered. So I want to thank you especially for taking us with you on your journey toward the discovery. This is very exciting, and we wish you the best of luck in actually finding Planet 9.
Thank you very much. It's great fun to be able to come give a talk to all you guys.
Well, thanks again. And I want to remind our audience that this series continues. Our next lecture is going to be February 3rd of next year in the evening, when we're going to have Dr. John Mather, the winner of the 2006 Nobel Prize in Physics, who's going to be talking about the history of the universe and how the James Webb Space Telescope, which Dr. Brown mentioned, the successor to the Hubble, for which he's the project scientist, how it's going to help us understand even better the history of how the universe and we came to be. So join us again, February 3rd, 2021, for another Silicon Valley astronomy lecture. Good night, everyone.